Dr. Rossberg is a friend of mine. We've been working together for more than 5 years. He's a PL expert, kind of Mr. Module, and now he works at Definity, which is a crypto startup.
Yeah, sorry. Yeah, this guy is Ben Titzer. So as he said, we worked together for 5 years, 6 years even, in the V8 team at Google. And in the end, he even was my boss, technically speaking, although I never listened to him.
That was a problem, actually. We have to talk about that later.
Okay, something happens. Let's try another port. It worked earlier. Let's try the other side. We have lots of ports.
This is really just in time.
No. Try this again. Huh. Okay.
This is really an unexpected development. This is not part of the plan.
So it worked like 10 minutes ago. So
Yeah. I think she ruined it, actually.
I ruined it. Yeah, it's my fault. You can blame me. I take responsibility. I think it's, yeah.
This is really not.
this is not good.
The screen went blue when mine was up.
Yeah, it doesn't
Tried
reckon.
rebooting.
Could do that. Yeah, I apologize for that.
It's not your fault, it's her fault.
Should I actually reboot? Maybe I really reboot. Huh?
You guys are actually 3 minutes early, so.
Ah. Should I try again?
Let's do it.
Now something happens. Ah,
Something
excellent.
happened. All right. Yes.
Excellent.
Okay, so that was just our bid for another round of applause. Thank you.
Ben? This won't work. Now it works.
Okay. What is WebAssembly? Actually, it's probably important to explain a little bit about it. It's a universal compilation target. We envision this as being something that all languages can compile to, with some friction, hopefully less friction. It is a new capability for the web, so we envision this being something where new types of applications that maybe have performance requirements, maybe they have new kinds of APIs, can come to the web and do new things that the web couldn't do before. You can think of it like a virtual instruction set architecture. It's like an abstract CPU. We've got all kinds of issues. But the idea is that it has a predictable performance model. So unlike JavaScript or JVM bytecode or something like that, where there could be a JIT or multiple JITs involved, WebAssembly is supposed to run at high speed and very predictable speed. But
Right, so there often is some confusion about what it actually is, and in particular what it is not. So we also want to put a slide on that actually debunks a couple of misunderstandings about what it is. So what it is not, we say it's not a value judgment about programming languages. So by that we mean it's not designed to fit a particular programming language or programming paradigm specifically, unlike previous other VM technologies you might be familiar with. So it's really completely agnostic to the language you compile to it. Our slogan is it's an abstraction over the hardware, not over a language. It's also, we say it's a language, but it's not a user-facing language. So as Ben said, it's meant to be a compilation target. So you use tools to generate the code. You can look at it, there's a text format, but you're not really supposed to write it. And it's designed to be a code format, not a compiler backend. So it's not a compiler IL or intermediate representation, not something like LLV in bitcode or something. That was not what we had in mind. It's really supposed to be a code format. And then one point I want to really emphasize is the whole design from the get-go was made such that it's not specific, not tied to the web at all. So we really were careful about making it a very generic general design that could work in various other environments.
okay, I think we skipped a slide.
You have to point it to this thing, I think, then it works better.
All right, so let's put it in a nutshell just to get an idea of what it actually is, because we talked about it in the abstract and what it's for. But basically, it's a really simple type of instruction set. There's only 4 data types: integers and floating point numbers, and 32-bit and 64-bit varieties of those. The kinds of operations that you can do are totally predictable: add, subtract, multiply, all of these types of pure operations on numbers. And you can convert between the different representations, and you can reinterpret the bits of an integer as a floating point number, for example. So functions in WebAssembly are not like functions. So the code is not organized, is organized into functions. It's not just like a big bag of instructions like you would get in x86. But the functions are organized into a single namespace. It's flat, so you don't have nested functions. All function calls have either static or dynamic binding. Static binding basically means you just call a function by its index. You can call a function indirectly, and that indirection just goes through a table. So it's not super advanced there. The main state of the program, as it is now, is basically what we call linear memory, which is basically a byte array. It's bounds checked, so every access within that byte array, if you go outside the bounds, you get an exception. And there are no implicit accesses to the memory. You have to use load and store instructions. The control flow in WebAssembly, even though it's a bytecode format, we've taken a sort of unique tack here, and it's actually structured. So you actually have to have blocks and ifs and loops that are properly nested. And the call stack, when you call functions, this is part of the sort of trusted state, and it's not explicitly exposed to the program.
Yeah, to make that a little bit more concrete, let's go through a really trivial example. So this is using the WebAssembly text format. So WebAssembly engine won't understand that, but you have tools to compile that down to the bytecode, the actual bytecode. And this text format happens to be an S-expression syntax, which was a historic accident, completely unprecedented. It was just something I made up when I wrote the reference interpreter the first time to have some way of expressing the AST, the familiar story. It stuck, and now that's the official format for WebAssembly. So what do we have here? This is a very simple function. And you can see a couple of things here. So first of all, you can see that it's explicitly typed. So for example, the function parameters is the result type. You have to annotate. A block can actually return a result. You have to annotate that as well. Local variables are also all typed. In this case, x is actually the parameter of the function, but you can also declare locals, which are basically virtual registers, and you have to declare them with the type. It's a stack machine. So you can see that here, like every instruction pushes and pops operands off the stack or onto the stack. So for example, the get local would push the value of the parameter onto the stack, and the if instruction then would pop it off as its condition that it's checking for. But interestingly, this stack, because everything is typed, the stack is really just a static thing in a way. It's usually completely compiled away. It's not something that is manifested at runtime, materialized at runtime. So as Ben said, the control flow is structured. You can see that here with the if instruction that has really nested blocks in it. And there are other forms like loops and plain blocks. And then, yeah, memory, you really have to load and store explicitly. There's like no implicit access to the memory. You really have to go through instruction like a CPU would. Here's a bit more abstract picture of the state we have in WebAssembly. So on the upper half, this is basically the state that is transparent to an application. So that is mainly just the linear memory. So an application can put in any sequence of bits and bytes in there. The engine won't care. All it does is a bounds check. Otherwise, it's completely uninterpreted bits as far as the engine is concerned. And then there is more delicate state, which is encapsulated inside the engine. So for example, the execution stack, as Ben also already said, is like not exposed at all. You can't access it. You can't address it. You can't take the address of anything on the stack. So this is completely hidden away from the actual code. Then there are functions. So of course, you can reference functions when you do a call, but there's no way to get to the code of the functions. So this is like similar as in other VMs. And then there's the indirect function table, which is really just a big table that has pointers to individual functions, which we use for indirect calls. And again, you can actually get and set the entries, but you cannot really see the table itself. Yeah.
So how did this all start? I believe in a deterministic universe with some probabilistic things underneath. So therefore, WebAssembly is actually a function of the things that came before it. So I want to talk about prehistory. So in 2011, Google released a technology called native client. This is basically a way to sandbox. You got to watch out for the edge there.
Yeah. I'm always on the edge.
It's basically a way to sandbox native code by doing some verification on the machine code. There was a later version of this, which was a portable version, which is basically packaged LVM bit code. In 2013, Mozilla, our frenemies, introduced a subset of JavaScript called ASM.js. This is basically a domain-specific language embedded in JavaScript, and it has a way to essentially verify the types so you can produce low-level code. And if you do that verification, then it's pretty easy to compile. I joined V8 in 2013, and we decided to start working on a new JIT compiler. I actually worked, that was my primary project, my kind of starter project, JIT. And that was, the idea was that we actually wanted to do better on ASM.js code. That was sort of like the first bar for us to do that, so we started working on that. This thing's really got some trickiness to it. Yeah, so in the course of working on ASM.js, there was always things that I didn't understand or didn't agree with. It was always a bit fluid and changed over time. So I started talking with one of the primary designers of that, who's Luke Wagner, who's one of the other co-inventors of WebAssembly at Mozilla. And we sort of had these backroom discussions. I didn't know that we weren't supposed to do that. So there's kind of like grassroots starting this project. By late 2014, this became basically already it was in our minds that we should go forward with designing a bytecode for this. By early 2015, I convinced my management to look the other way while I did the side project that was not efficiently blessed. Other teams inside of Google got wind of this, including the NACL team. They decided to join forces with us. They came with a slightly different set of expertise, and so we had slightly different worldviews that had to be reconciled, which I'll talk about a bit later. It's actually some of the interesting parts here. By May 2015, we had started to do this marketing via alcohol. So I don't know if you know Phil Pizzello is also a part of this community. He works at Apple on a JavaScript engine, and he's been a friend of mine ever since my Purdue days. And we basically got him drunk and told him it was a great idea. And with his blessing and other engineers in their organization, and also with Luke's work to talk to Microsoft engineers that he knew, we were all ready to announce that we were working together on this. That was pretty unprecedented that 4 companies, basically all the engineers got together and decided, hey, let's do this new thing. So that was actually a pretty big accomplishment, I think.
Yeah, so at that point, we officially formed a W3C group. So all the design and discussions from then on were kind of in the open, more or less. We still had some meetings, face-to-face meetings in the early days where we tried to move forward, but most of the stuff is actually visible, all the history. So yeah, after that, we were basically busy building implementations, prototypes. So by mid-15, we had one running in V8 or as a patch to V8, and Firefox also had a version. In the summer of the same year, I came in and started implemented the reference interpreter in OCaml, which was based on the V8 prototype and already had the full semantics in it, and included a whole test suite. So that was what we used afterwards to check consistency between implementations. And then throughout the rest of that year and the next year, basically everybody was busy doing implementations. There were lots of design discussions still moving things around. Some of them we're going to talk about. And in early 16 at the Game Developers Conference in San Francisco, we were able to actually showcase the first demo, like a little 3D game that ran in 3 of the 4 browsers already. So Chrome, Firefox, and Edge already could execute the same demo, the exact same code. And yeah, in parallel to that, I specifically started working on the formalization, and in the end of 16, we submitted a paper to PLDI, which included the formalization and the entire design motivation for WebAssembly and some evaluation and stuff. And this was work with lots of authors on it, like all the browsers involved actually participated in this paper. So this was another great step in collaboration, actually. Yeah, and then in last year, in March, Firefox and Chrome finally shipped. So, and a little bit later, also Safari and Edge shipped. So since last summer, this is actually a technology that is real and available to everybody who's running a recent browser.
Okay, so I want to talk a little bit about performance versus portability, a little bit about what I mentioned with this clash of worldviews. It was not entirely clear to everybody from the outset exactly what this should look like, exactly what the properties should be. There's open design problems, and there was open design sort of pressure. So that manifested in a couple of difficult discussions, long discussions, and actually it's good that those discussions took place so that everybody could understand all the dimensions of the problem. In particular, some of those things that we discussed were like, should WebAssembly have undefined behavior? There's a reason that C has undefined behavior, because it has to be portable across many machines. But should WebAssembly have the same thing? Should it be completely deterministic, or should we allow non-determinism? C also has this horrible thing which they sometimes refer to as nasal demons, which is not only undefined behavior that produces non-deterministic results, it could actually do anything, including launching missiles. That was shot down pretty early, thankfully, when we were talking about WebAssembly. But other things that we had to get into the details of, like, should we support all IEEE 754 floating point standard, or should we do something that diverges for better performance? The memory actually has a page size. We actually had more than an hour discussion about what the page size of the memory should be. And also, when we get into the details of validation, there must have been dozens of hours, at least months of discussions about what that should look like. Another point of contention, quite some time, and it's maybe not everybody's happy with the solution that we came up with, was how we represent control flow in WebAssembly and what the stack machine looks like. So in the beginning, so as you saw from the design, we have structured control flow and we don't have go-tos. So you can't construct improper loops, and you need to actually create blocks that are properly nested. We started actually with the idea that we just wanted to have an AST, because at least I and Andreas thought of this as a language, and languages typically have ASTs, and you just encode the AST into the binary. That also fit with the idea that we're coming from ASM.js, which is a JavaScript parse tree, basically. But we evolved in 2 steps from going from a pre-order encoding of that to a post-order encoding of that, and eventually to a stack machine. And each of those steps was justified by data. The reason we moved to post-order encoding is because it turned out to be a lot faster to parse. And then the reason we moved to a stack machine was actually easier to evolve to multiple values.
Yeah, and then another point of contention a little bit was like, how much rigor should we apply to the design and the specification and the language standard as such. So as I said, we actually did the formalization, and there was strong support for that from some key people in the project, like Ben and Luke and me, obviously. But not everybody liked the idea or thought it was worthwhile doing. But so we had some struggle over that as well, but in the end, we did it, and I think as far as we know, it's like really the first mainstream language I'm aware of that was designed hand in hand with a complete formalization. And as far, from my perspective at least, that had various benefits, in particular leading to a much cleaner and simpler design in the end because of the feedback loop we had with the actual design discussions. And this was not just a formalization on paper, it's now actually part of the official language standard. So the standard, the specification of the language is actually centered around the formalization. It's not just an appendix, it's a core part of the specification. Oh, this is me. Right. So this is how it happened. So WebAssembly ships. We are here now. So what did we achieve? Well, to go into, before we can go into that, we actually should state what our goals were. So we designed this code format, and obviously we had some things in mind there. And so here's like a long list of individual properties that we wanted to have, like it should be independent of hardware, of language, and so on and so forth. It should be fast to execute. So Ben, I think, mentioned in the beginning that the original motivation was something to be close to native code execution. And yeah, we really wanted to have, at least at some point, we agreed that we want to have a deterministic semantics and all these things. So this is about the semantics of the language. But this, like, the main motivation for WebAssembly originally was the web. And if you're familiar with the web and, for example, to how much length JavaScript programmers go to minimize their code size, right? They run tools called uglify and all these things just to save individual characters in their source code. So every byte matters when you transfer code over the wire. So the representation was another big concern, like in particular that the code is compact, but also that you can decode and compile it fast. So one central design point of WebAssembly actually is that it's designed to be just-in-time compiled, not to be interpreted. So some design decisions actually were to meet this goal that it's fast to compile. And of course, we also wanted to be extensible, and we wanted to be streamable, which means that while you're still downloading the code, you can already start compiling some of the functions, and you can compile them in parallel and all these things. And all that was important to us, and it turned out that none of the pre-existing technologies would meet all these requirements. Sir.
Yes, sir. Did we deliver? Oh, you make me deliver it. Okay. Yeah, I think on many of these things that we did deliver, and the ones that we didn't, I'm not going to mention. So in particular, we really wanted to have a single pass decode and validate. Basically, you run through the bytes once, you don't ever have to loop back. That means that you can basically decode and validate at line speeds, so gigabit speeds, with a single thread on today's CPUs. So working on compilers and being a compiler person, in particular working with SSA, I wanted to make sure that we could get into our compiler IR with a single pass. So turbofan, basically, as we come along and look at every single byte, we can generate corresponding turbofan graph nodes. And by the time we get to the last byte, the graph is done, and we're ready to go compile. I don't think you can do better than that. I don't think you can have a zero-pass translation. For the speed of compilation, this depends a lot on compiler details. So most of this, the numbers that you get here, they really depend on your compiler architecture. It's not really a function of WebAssembly itself. But for turbofan, we can compile roughly a megabyte or 2 megabytes a second, so we can throw multiple threads at this. This is pretty good if you want to start up like a 1 or 2 or 10 megabyte module. You get going in a couple seconds. But that's actually not fast enough for really big applications or for mobile devices. So one can imagine actually just generating code as you see each byte. So as you decode and validate, you can just generate machine code. It was actually designed to be able to do this. So we actually built, and also Mozilla also built a baseline compiler. So this ships as the first tier. This is essentially 5 to 10x improvement in compilation speed, which means that you save 5 to 10x in startup time. And then for the actual performance of the generated code, so the runtime performance, the idea is that we wanted to get in within 20%. Of course, this is a ballpark, versus like something like 80% slower for ASM.js. So we had a lower bar to jump over. This is a graph from our PLDI paper. So these results are basically comparing with native code. It's also comparing 2 VMs. So if you see this light blue bar, that's actually the difference between 2 VMs. And one VM's faster or slower, so we can hide whether Chrome versus Firefox, so we don't have to talk about that. But the black line there is native code performance. Anything lower means that we're somehow faster. And those are mostly just some where we got lucky versus GCC. And anything above that is where we're slower. So you can see that there's really only 1 or 2 outliers where we're more than 50% slower or something like that. So that 20% number actually manifests in some kind of distribution. For code size, we also measured this carefully too. This is versus ASM.js code. I think this is compressed ASM.js code. And also versus native code.
Yeah, so that was about the implementation, and the other side of the project was the formal semantics, which I already mentioned. So as I said, we really set out to have a complete formal semantics, and we have that. It's really complete from starting from decoding of the binary format to execution. Everything is 100% formalized. I think it's even more complete and unambiguous than the standard ML definition, I'm proud to say. So that also implies that there's no undefined behavior. So Ben mentioned that in the beginning, we really set out to not have any of that at all. So everything is fully defined. And we have a proof of that. And to do this, we really wanted to showcase all these techniques that have been developed in academia over the last, I think, 3-4 decades actually, about formalizing programming languages and their semantics, and show that this is actually usable in practice. So we really wanted to use these techniques off the shelf and not have to invent anything fancy. Yeah, and there's a proof of soundness, and there's a proof of soundness not just on paper, but it's actually machine verified. So specifically, what we used for validation is really just a type system. It's a dead simply type system, almost embarrassingly simple. By design, because it has to be fast, right? Like we have to do very fast validation. It's just using standard type deduction, natural deduction rules. Similarly, for the execution, the operational semantics, we just use small step reduction rules over a stack machine in a somewhat interesting way, but it's still like really mostly straightforward. And then there is not just one mechanization, there are actually 3 mechanizations in progress right now. So one is actually published, that's the one in Isabel that was done by Konrad Watt in Cambridge. He's a student of Peter Sewell. And the COG one is done at MPI currently, and I don't know much about the K one, but somebody's working on that as well. So if all this works out, we actually have multiple mechanizations of this formalization. And the one in Isabel specifically, Konrad already started that when the PLDI paper was still under review, so he discovered like a couple of minor bugs in the rules, so that was actually valuable. So just want to flash this at you to show off how easy it is. This one page is the entire operational semantics of WebAssembly. This is again from our paper. And this page is the entire type system, the complete validation. And you might be like, find this more impressive. So you don't have to read that, don't worry, but just to show it off. So if you compare this to, for example, the JVM does bytecode verification. This roughly corresponds to this, right? To that, what we call validation. And the JVM bytecode verification specification has 160 pages. And this is like 3/4 of a page in our paper. So there's really a value of doing formalization while you design stuff because it leads to a much simpler thing. Right.
Okay, so this was started as a browser project. This is called WebAssembly because it started in the web. But it's really an open standard. So we work within the W3C, and we work in the open on GitHub. What that means is that it's been a magnet for crazies. Actually, no. There's been many people who have contributed positively from the open web, and only a couple of crazies. But that also means that all of our we are the crazies. So that means that all of our dirty laundry and all the issues, anything that we've discussed is pretty much there in the public record. There have been a couple of sort of dark, smoky room discussions between the 4 browsers where many design, a few people have been there actually in the audience, but where many design things were finalized, but really we committed to doing this in the open and driving it forward in the open. So anybody can contribute. It also means that it's not proprietary. It means that this is really something which is anybody can use. It's not encumbered by copyrights and patents. W3C has patent protection where people who, organizations who choose to join, they sort of sign up to sort of share and everybody's friends. So nobody sues anybody's pants off.
Not yet.
Not yet. Well, that hasn't been tested yet. So a lot of people are already using this. Google is already shipping products with it. Some companies are betting their future on it. And yeah, there's already lots of stuff out there.
So yeah, this is the current status. So we shipped WebAssembly 1.0, we call it. Like also the working title was the MVP, the minimal viable product. You know, this is management speak for doesn't completely suck. But this was just, there's a larger plan here. So there's a rough roadmap. So version 1 was really specifically targeted at low-level languages. So we consciously delimited the scope of version 1 to support low-level languages as well, like C++. basically to be able to deprecate and replace ASM.js as a native client. And because the main users in the first round are these pre-existing applications like games and 3D applications that just have their existing C++ code base and just want to cross-compile to the web. So this was our first goal, to make that work. But it was always clear that we want to go beyond that. So for version 2, just as working title, it's kind of what we're working on now. So there's a pipeline of proposals now to support high-level languages better. And hopefully that most of that will ship around next year. So it's not really like a strict version. It's more like a continuous thing, but just to give you an idea. And then there's something that might be further out there, which is to support dynamic languages better. We don't really have discussed that all that much, and this is a bit more vague, but I would imagine that this would be like a further step because there's additional complication there, obviously. So yeah, we have this nice specification and implementation and formalization and all that, but we want to evolve it. And why we evolve it, we want to maintain all these nice properties. So we actually have a pretty elaborate proposal process to evolve the language. So if you want to get something into WebAssembly, a new feature, then you have to make a proposal, and this proposal has to go through various stages with the W3C working group. And along these stages, you have to come up with various deliverables. So one of the first things you have to come up with is actually spec text, the pros for the spec. At some point, you actually also have to come up with formalization of your feature, or at least you have to find somebody who does that for you. Right? Then you have to extend the reference interpreter with the respective feature and provide a comprehensive test suite. So you also have to extend the test suite such that the reference interpreter actually works on it. And then you have to convince at least two people working on in two different production engines to implement that feature. So that it's tried out in production, we know that it actually is implementable and realistic and efficient. And of course, these also have to pass the test suite and all that. And only if, once you get through all these things, once you deliver all these things, your feature can get into the standard. And of course, the working group also has to approve of it, obviously, but nothing matters if you don't deliver these things. So there are various features in the pipeline right now for this like high-level language support. Here's a short list. This is not a complete list, but this is like the kind of the major features, I would say. So we're gonna walk through some of these. And the first one being threads, and Ben has some interesting things to say about that.
Sure. So some languages, low-level languages like C and C++, they have the ability to have essentially unstructured shared memory concurrency. So you can roughly think of that as the pthreads library. So there's tons of existing code in C++ that people want to bring to the web through WebAssembly, and just being able to emulate pthreads on top of that means that you can essentially hit a button and that will run on the web. So in order to do that, we need to be able to support C++'s atomic operations and its synchronization primitives. So we add instructions to WebAssembly for atomic shared memory access that have the proper concurrency semantics. There's a huge challenge there in that there's this giant unsolved problem called how to specify weak memory models. So we're leaning on our friends from academia, in particular Conrad, who Andreas mentioned before, to be able to formalize a memory model for WebAssembly that makes sense. Implementation work. Actually, you can imagine taking a JavaScript VM, which is, let's say, 400,000 lines of code or more, designed for a single-threaded language, and making it multi-threaded and being able to share code across multiple domains. That's actually a lot of engineering work, but there's this small thing called Spectre, which, raise your hand if you did not hear of Spectre. All right. Okay, there's a couple of people. Spectre is a vulnerability in the very bottom of the computational stack, which is in every CPU that does speculation. There's security bugs. That's a problem. So I don't want to talk long about Spectre. I spent quite some time working on it. In fact, I think it damaged my brain in some way. But In response to Spectre, all of the browsers disabled shared memory. And the reason for that is that it's easy to build a high-precision timer using shared memory and concurrency. And that high-precision timer is how you can mount attacks that leak information through Spectre. So one quick mitigation is to just remove shared memory that was there before in the form of shared array buffer. So VM teams across the industry actually did offensive research into Spectre before it was disclosed. It was ongoing for quite some months. That actually took a lot of engineering time. That was away from doing features like threads. I'm going to talk a little bit about that in a workshop that's later this week on Wednesday. I encourage you to attend that if you're interested. It also meant compiler mitigation work. So even though the hardware is broken, there are a few things that we can do in software to take away some of those information leaks. It's not complete. We know that. This is not a solved problem. And that's really unfortunate for everybody who uses computers.
Yeah. There are other not entirely solved problems in terms of features, but I think we're mostly got them now. So one interesting feature we want to add, at least I think for this audience it's supposed to be interesting, is tail calls. So I don't know who's familiar with the sad story of tail calls in JavaScript. So I witnessed that kind of disaster firsthand when I was still on the JavaScript committee. Sorry for that. And then when we started talking about tail calls in WebAssembly, I kind of had like a real deja vu, because actually the same kind of discussion started again all over. So let me first say, why do we want tail calls? Obviously, for certain languages that need them, but also there are various compilation techniques you want to use that really benefit from being able to perform tail calls. So it's not just on the language level, it's also on the compilation level. And the idea how we wanted to support them is really just by adding dedicated instructions. So not require the existing call instructions to perform tail call elimination, but actually have separate instructions that are essentially a combination of a call and a return. So relatively simple design. Turns out, though, that it's tricky to implement, at least on some platforms, and the primary one being Microsoft, because Microsoft Windows has a specific ABI with very specific calling conventions, and these calling conventions are designed after C++, obviously, so they want to support bar arcs and all that, so it means they are, the arguments are caller pop, which is unfortunately not compatible with tail calls. So you can work around that in most cases, but not in all of them. And so Microsoft doesn't want to change their calling conventions because they actually use that consistently throughout all their languages and all their tools, right? So it's important for them that all their tools like debuggers and profilers and stuff can really interoperate across all these languages. So it's really understandable that they are very reluctant to doing that. So in most cases, they can work around that, but there's like this one case when you perform a tail call to a function that has more argument than the caller that they can't efficiently handle. So after some banging heads, we actually agreed that, oh, you know, this might not be a problem. So we can just say this, so you can make the observation that the number of times this case can happen is actually bounded. It's finitely bounded because there is a maximum number of arguments in your program, right? So if you have a call chain and you don't just consider the current caller, but all the callers before, and you remember what the largest one was, then you can only grow the argument size a finite number of times. So that means that actually we can allow these cases to be implemented as non-tail calls and just amortize this cost. This will not break the actual guarantee you want from tail calls that any unbounded sequence of tail calls will not blow the stack, right? It's only a finite number of calls that will actually take up space. So once we agreed that this is fine, we were able to move forward with that. Another thing we want to add, working on, is exceptions. I think I will skip over that. Basically, the current design is roughly kind of like ML exceptions. And there's implementation ongoing on Chrome. Another interesting thing is, well, let's call it stack switching. So that is the ability to somehow create new stacks and switch between them, call stacks. And you want that, some feature like that to be able to implement all these control abstractions that keep popping up in languages nowadays. So ancient ones like coroutines, or if you want to implement your own lightweight threads. But also these things like generators and async await that you see in modern languages now. They're really all just control abstractions that do some stack switching, or more formally, semantically, they need some form of delimited continuations. So this is something we want to add. We don't really have a design yet. We have investigated effect handlers, for example, as some possible approach to doing that, but there's no concrete proposal yet. But this is definitely a feature that we need to add at some point. And then there's a real big feature, probably the most complicated one, and the one that moves us furthest away from being an assembly language, is adding garbage collection, or as Ben prefers to call it, managed objects.
Well, garbage collection is so negative. I mean, you want to talk about management is positive, right? As a manager.
Yeah, as a manager, you should say that. Yeah, so we want to add garbage collection to really support all these 95% of languages out there that actually need garbage collection nowadays, right? Other than Rust, there's no modern language that would not use garbage collection. So you obviously want something like that, and it seems kind of crazy, for example, on the web, if every application would have to ship its own runtime with its own garbage collector. And all these, at least in browsers, all these JavaScript VMs, so WebAssembly is always implemented as part of the existing JavaScript VMs. They already have this like super highly tuned garbage collectors in them, so why not enable using these in WebAssembly? So that is one part of the motivation. There's actually a second part of the motivation for garbage collection, which is easier, more seamless interoperability with your hosting environment. So on the browser, for example, you want to be able to pass around references to DOM objects, for example. Right now, this is not possible, right? Because as you saw in the beginning, we just have 4 basic types, which are numbers. So what you have to do right now is actually to create a reference to a DOM object inside WebAssembly. You somehow have to map it to an integer on the boundary. You have to maintain this bijection. You have to implement some form of garbage collection on this bijection as kind of like a weak map. And this is what applications are actually doing today, but as you can imagine, this is not very convenient nor particularly efficient. So if we allow host reference to actually flow in and through WebAssembly, then of course we also need at least some minimal support for garbage collection. So the way we want to bring this into the language, very roughly superficially, is just like sticking to the low-level nature of WebAssembly. So there's no object model or anything like that. You just have the ability to allocate structs and arrays at the lowest level. So really just tuples. And then any language that wants to compile into that has to map their own kind of object layout into this. And then you have instructions for allocating and for accessing these things. I already said that, so this is also to reuse the existing GCs. And so operationally, this is all simple, and also in terms of implementation, because we can just reuse what's there, it should not...
Yeah, it's just simple. Yeah.
It's simple, as everything is simple in JavaScript VMs.
Also in V8.
But it turns out that it's actually not that simple on the static part of the design. So how do we type this, right? So one thing with WebAssembly is it's kind of like in a weird spot, and this feature specifically is deep in the tension between these 3 things, which is like we absolutely have to be safe. So safety is an absolute property we have to maintain. We want to be fast, so performance is the other thing. And it should be simple enough so that compilers can target it easily. So, and these 3 features, as you can imagine, are like really in conflict with each other. Where exactly you put like the design there is like pretty much an open question. And once you start thinking about the design, you immediately collect like 2 pages of bullet points of things that you need to include or think about at least. So we're working on it, but this is probably going to take a little bit of time. SIMD, I think we skip over that, or you want to say something about SIMD?
I'll just mention briefly. So some types of applications, such as video codecs and things like that, really want to get every ounce of performance out of the hardware. So the way to do this across many different CPUs that have vector instructions is really kind of specifying the intersection of all of those. So we basically decided to expose a set of 128-bit SIMD instructions.
Like 200 instructions only.
It's only 200 instructions. The problem with that is that it's 200 instructions, and it will probably become 400 instructions, and then 800 instructions as we get larger and larger vectors. So one thing I want to talk about is that it was a very deliberate design decision to have layers in WebAssembly. It's called Web and Assembly, but as you can see, it's not just for the web. So there's this idea that there's this core execution thing, which is like a CPU, which is all the instructions that you need, all the bytecodes that you need to run. And then the APIs that you get around that, so the things that you might want to access in the web, or like get to the DOM or get to JavaScript or things like that. You can also think of an alternate set of embeddings. And we call these embeddings, and we actually specify them as explicit layers in the way the specification text is written. There's already other embeddings have started to pop up that maybe we should start to care about and bless. So mobile platforms. There's a company called Fastly that's pushing WebAssembly out to the edge of their CDN.
I think Tyler's actually here. He's giving a talk this week about it.
It's right there. Cool. It's only $50 for that. Also, I know this crazy guy who works for Dfinity. They're working on blockchain, cloud computing, and using WebAssembly. And embedded devices, always you have some APIs that you want to drive, and you can use it as a portable assembly language. And standalone implementations, if you want to get portability across hardware, and just have different APIs that you can embed into. All right, so this is our summary slide. So WebAssembly is designed to be an efficient, universal, safe, and sandbox code format. All of those things are really great, and we want to keep those going forward. Key thing to remember is that this is an open, public, standard process. Anybody can contribute, including all the crazies on the internet that I mentioned before. I hope the people in this room would not fall into that category. But that means that it's not dominant. It may be heavy on browser and implementation people participating in that process, but anybody can offer ideas. And I think that's really valuable, so that it's not really just controlled by one actor.
Yeah, and we now see participation actually in the working group and the community group from non-browser users and people. Like, I mean, I switched side myself, but there are others from these communities, especially, I think, content delivery networks and cloud computing people who use this as their sandboxing platform, essentially. So yeah, and we also want to maintain the formal rigor we have applied so far and the level of machine verification, even if that's possible, although that always requires some volunteers. So the machine verification part is not a requirement if you propose a feature. I think we're not quite there yet. I think we already made quite a leap with respect to the requirements we make now for new features and the level of rigor. I would love to see a future where you actually have to do all the machine verification as well as part of the language design work, but I don't think we're there yet. I don't think that's realistic yet to require that. So that's not a requirement yet. Yeah, and then basically the slogan you can take away from this talk is, we call it WebAssembly. This is kind of for a historic reason. I mean, the web was our way to get the foot in the door with this technology and convince management that it's valuable. But I think all of us actually had something more general in mind when we started working on this, and we really want this to make this a general computation platform that could replace things like the JVM as a runtime you can use to compile your languages to. And yeah, it's also not really just an assembly language anymore when you consider some of these more high-level features. We still try to keep it as low-level as possible, but no lower. So because of the safety requirements and things like that, portability requirements, you have to always make a certain trade-off in terms of how low-level it really is. And that's, I think, all we have to say about it for now.
Is this working? Before we get to questions, I have one really small logistical announcement. If you only received the crayon badge and not like this other paper one, which is probably half of the people in the room, at some point, not right away, head back to the registration desk and grab the paper one because it has your lunch tickets and your party tickets, just so that, you guys can go and have lunch. So it's important that you go grab that. Otherwise, we have 10 minutes for questions, so.
Hello, I'm Simon Peyton-Jones. So I just wanted to ask one question about your kind of positioning slide, in which you said what it is not. You said it's not a compiler backend, but I think you are seeing it as a compiler target language. You're not. You want to compile high-level languages into it. So what's that difference? And then could you contrast a bit what your, particularly by the time you got to the end of your talk, I was thinking, okay, so does that put you in direct competition with LLVM? And where, how do you, I mean, competition is a good thing, right? Diversity is good, but then there's, apart from compactness, right, where are you, how would you express the trade-off with LLVM?
So there are a couple of things. First of all, compiler IRs are, as you say, not usually designed to be compact. There's some other issues with LLVM, for example, that it doesn't actually have a fully specified semantics nor a portable semantics. And it actually doesn't even have a stable semantics, right? They keep changing it all the time. So these are other things, I don't know what other reasons were there. We had a couple of other problems.
I'll just mention, so Pinnacle was exactly that. It was LLVM bitcode as the portable format. And I think the reason for this is basically you get into backend optimization requirements, like sneaking into the bytecode that really aren't there. Like, we really just want to be succinct. And so the distinction is between succinctness and being useful for compiler optimizations. So, okay.
I have plenty more.
Phil Wadler.
Yeah.
Phil Wadler, University of Edinburgh and IOHK. So for my sins, at one point I worked on xQuery, which also had a formal spec. But I think your claim is still accurate because I don't think xQuery can claim to be widely used. So in some ways they were very happy with us because there's a proposal put out and we formalized it. We found 10 issues in it. And they went, okay, there's something to this formalization. So they let us put the formalization in the spec, but they said it's non-normative. If the formalization and the English prose differ, it's the English prose that's correct. So we weren't very happy with that. But it makes me want to ask you, so what happened with you guys?
So, yeah, that's a good question. So basically, I wrote this spec based on the formalization. I wrote the language spec, and the way I did it is I took all the rules, and then I created text renderings of the rules, right? So the text prose form of the spec is really just supposed to be completely equivalent to the rules, and they're next to each other, so you can really read off the text of the rules. It doesn't always work out nicely. Like, for example, I realized small step reduction semantics is kind of weird to explain in a natural way, right? You don't usually think about it as individual rewritings you do. So there's a bit of wiggle room I took there. But yeah, basically the answer to your question is if there's an inconsistency, it's a bug in the spec, and it has to be resolved as every other bug, right? Yeah. So both are normative in that sense.
There's a question there. Over there.
Ben Lifshitz, Brave Browser in Imperial College London. So if you look at something like Node.js, it seems to be everywhere. Client, server, like in space, toasters, refrigerators, things like that. So inspirationally speaking, what is your inspiration for where you want to see WebAssembly in a few years?
Where shouldn't it go?
Be specific.
I definitely see it as something that could replace the Java bytecode as something that you would compile to, obviously. I've kind of had the mantra in the back of my mind, it's easy to be universal the more low level that you are. You can kind of see that in that it's basically just a CPU with arithmetic. So there's no reason why you couldn't use that as your default compilation target, and then hardware underneath you basically has a VM on top of it. So I don't know why you couldn't, for example, implement a POSIX API, and then Unix was literally just WebAssembly with some API, and then the future of Unix wouldn't matter what CPU you're on. As far as languages compiling to it, it's really a difficult design problem. We've discussed it a lot, and it's how to make this managed version of it actually support all languages that compile to it well. There's challenges in compiling Go. There's challenges in compiling languages that have interior pointers and things like that. So designing the next level for languages compiling to that's a hard problem that I don't know that we can solve, but I think it would be really useful if we did solve that. So we need some help. Maybe you can offer your opinion.
I think there's no real limitation to where it could be useful, and that was kind of the goal, right? To make something that is really universal enough that doesn't bake in certain assumptions about the environment you're running in. So, yeah, really, mostly what you said, right? It should really be useful almost anywhere. And both on the web, it could offset some of the uses of JavaScript today, especially when you need performance. I think what's going on with JavaScript around performance is kind of crazy and not really sustainable. So this is a much simpler way to achieve that. But also outside the web. So I don't know how many questions we get all the time about the standalone implementation of WebAssembly. So people can just write their compilers and don't have to worry about things like, I don't know, instruction selection anymore, right? So this was actually my kind of plan, right? I love implementing languages, but I hate writing compiler backends and runtimes. I don't want to get into that business. So I want to design, this nice interface and let some other really smart people do all the ugly work for me.
It's not ugly, come on.
And can focus on the interesting stuff from my perspective, of course. So I think, yeah, this is one direction I particularly care about.
So one other thing I want to mention about that. So we're currently kind of at a crossroads where we kind of have to get these managed objects done soon. Otherwise, we're going to grow dependencies on languages that are compiling in their own GCs. And so you end up with this lifetime problem, which is kind of inherent in having a low-level language and a high-level language, which Andreas alluded to, is having this interface where you have weak references and arrays and things like that. In the limit, what you need to have is a combined garbage collector, which collects things which are in the managed heap, and also traces through the things that are in the unmanaged heap. So we ran into this problem constantly in implementing Chrome. Chrome is written in C++, but it's actually got JavaScript objects that those are allocated on the heap. We actually have a tracer that goes through both heaps. You end up with the same problem if you have WebAssembly that have languages that are compiled to WebAssembly bits. And actually, we don't want to go there because then we have to specify this cooperative tracing. So we actually want to solve this problem as soon as possible so that languages that would bring their GCs just don't and instead use this. Otherwise, we're going to end up with just 7 levels of hell of this. Anyway. Next question.
Hi. I think that's me. Yeah, I actually did that 7th level of hell in Firefox a long time ago. You don't want to go there. So you mentioned, I have 3 quick questions. They're all pretty specific. Graydon Hoare, Apple. First, you mentioned that a lot of people have asked you about tooling on the WebAssembly as input side. Where's that at? Is there a tool chain out there somewhere that will AOT compile? If I feed a block of WebAssembly into a tool that produces an ELF binary or a Mako binary or something that can then run, free language implementers from having to write their
You mean
front end?
offline as like?
Yeah, offline. Yeah, rather than as a JIT. I mean, you've got these JIT implementations that are embedded in web browsers. They're great JITs, blah blah blah. But that's not most use cases for most programs. Maybe by volume it is these days, but.
So I don't think there is a tool chain for that right now. We'd love to see one, and we know that many people would love to see one. We don't have the capacities to work on that ourselves, but I mean the standard is open, so everybody could. I know that actually the OCaml Labs folks, they just recently have started a project on compiling WebAssembly to x86 through the OCaml backend.
Yeah, we'll go through another backend.
So maybe that's one first tool in that direction. But other than that, yeah, there isn't much out there yet. In general, there isn't much out there yet that has production quality that actually targets WebAssembly. I mean, it's pretty new technology. So the main compilation stack that we have, or the WebAssembly project team has worked on itself with the C++ pipeline starting through mscripten, right? And the Rust team has done a lot of work, as you probably know.
Yep.
But these are the main two compiler pipelines, I think, that are really available right now on production quality level. But we really hope that more will come out soon.
Okay.
But, I mean, that's only under our control to a certain extent.
Of course.
There is a standalone implementation which is called WAVM, but it's basically just somebody's solo project. It uses LVM as its code generator. So it's basically just nobody is supporting a production quality version of the thing that you mentioned.
Can I, two little minor, okay. First of all, your MVP wasn't 32, if I understand correctly. What happened to 64? Where is it? And secondly, could you just talk a little bit about sources of non-determinism in the spec, if there are any, and ambiguity in encoding as well? If either of those have
Yeah,
any room for
so
them?
you mean 64-bit memories?
Yeah.
Basically, it's a chicken and the egg problem. We know that people will eventually want to have 64-bit memories, but mostly, at least in the browser, we're stuck at 2 gigs. That's because of V8 limitations, which we're working on. But up to 4 gigs, we're kind of okay keeping it there now, but 64-bit memories will require like new opcodes because everything is typed, right? And we don't want to have overloading. Oh, like, I don't know. I can't promise anything.
I mean, for the web alone, it's actually not particularly useful, right? Because at least on mobile, you don't have that amount of memory anyway. But to answer the other part of your question about non-determinism, yeah, I think we took out that slide. So there's actually almost no non-determinism right now because we don't have threads yet. There's one tiny bit in the specification where we basically had to give in to the reality of hardware, which is the exact bit patterns of nans, of floating point nans. So when an instruction generates a nan, then we don't specify all the bits precisely. So we allow some different bit patterns to arise there. And the reason was that so unfortunately IEEE doesn't actually specify that, and hardware chooses different things. So we could have required normalization there, but that would actually be somewhat expensive. And this is a bit unfortunate. So for example, I work in this blockchain context now. We want to use WebAssembly as our execution platform, and there you do replicated computation. So it has to be completely deterministic. So we actually have to inject normalization code now if you use floats and nans. But yeah, right now this is really the only tiny bit of non-determinism we have. And then of course, if you do things like calls into the host environment, then of course all bets are off. And of course, resource limitations is the third kind of thing that you can't really guarantee. So with threads, you obviously have the obvious non-determinism that they induce, but yeah, we want to make sure that there's no other hidden non-determinism coming in. So as long as you only have one thread, we really want to maintain the level of determinism we have now. Although I'm not entirely sure what's up with SIMD there. Like that might add.
I don't think it adds anything new.
I remember some discussions about there where they considered under-specifying certain things.
It has different rounding modes. Actually, sorry, yes, it does have some non-determinism. For different hardware has different default rounding modes, and we actually allow them to do flush to 0, for example.
SIMD.
Yeah, in SIMD. Also for resource limitations, we actually specify sort of a gentleman's agreement on how big of modules and how many functions you can have, so that essentially we hope that all engines will basically enforce, okay, you can only have a module which is a gigabyte with 1 million functions, for example, just so that if you trip some engine limitation, you trip them at the same point on all engines.
But that's just static limitations.
Those are static limitations.
All right, so we can have one more question.
Okay. Peter Contio from Recruit Communications. First of all, thanks for your amazing work. My question is, what is the amount of runtime checks you have to bake in to keep your soundness properties? And I'm thinking especially the indirect function calls and such.
Yeah, so for accessing the memory, we have to do bounds checks. So the memory is 32 bits. So if you run on a 64-bit machine, we just reserve enough address space so that if you're out of bounds, you always use a 32-bit index because it's typed in the bytecode. So if you go outside of the bounds, you just cause a page fault. So that basically is a 0 cost for accessing memory. If we have 64-bit memory, I think I found a way that we can do it without an actual bounds check, but with 2 memory accesses. But otherwise, it would be a bounds check, which is essentially compare and branch. For indirect function calls, basically, we have to bounds check that you're within the bounds of the table. And we have to load something which tells you the signature of the function at that index in the table and compare it. So it's basically a couple of loads and a bounds check and a compare. So it's on the order of like 10 instructions for an indirect function call. We have the ability that you can specify the type of functions in a table and have multiple tables, so that eventually we would allow typed tables, so you don't have to do that additional type check, and then it's only just a bounds check basically.
Yeah, I mean, one thing to realize is that, so the indirect function table is heterogeneous, right? So it's, it can contain functions of different types. And the reason it was done that way is really to have an ability to emulate function pointers in C, right? So because they have one single address space. So that kind of forced this design on us. But in the future, like one part of in the direction of the GC proposal is to actually have type function references simply, so that you can call through that. And if you're using a type language that doesn't have function pointers as a low-level thing, then you wouldn't even use the call indirect instruction. You would just use these function references, and they're fully typed and no checks whatsoever.
Well, let's thank our speakers.